Hey everybody, Dr. A here, and in this video we're going to be exploring another example of computing the moment of inertia using the integral formulation. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's jump into it.
In this video, we are being asked to compute the moment of inertia about the y-axis. So we're given this area shape here, okay? And we notice that we have this not so simple shape this time. We have an area that is formed by a function y equals square root of x, and we are given x equals 1 meter and y equals 1 meter as kind of some boundaries on this. So how do we tackle this? Well, again, we take the same approach we've been taking. We use this integral form. But this time, again, notice that we're being asked to compute the moment of inertia about a y-axis. So here we're going to say I sub y equals the integral over the area x squared dA. Now, if you remember our recommendation, we want to orient dA vertically this time. Now remember our idea was to orient dA parallel to the axis that we want to compute I about. So in this case, our dA is going to be oriented vertically like this, okay? So that's some kind of differential area dA, a slice, and it's going to have a width of dx, and it has a height of something. Well, what do you think this height is right here? This is, of course, y, but guess what? We have a function for y, right? So whether your dA slice is up here, okay, maybe it's here, maybe it's down here, whatever, the height of your differential area, this little rectangle, is y. It's your function value, okay? So so I can write that over here. I can say dA equals y dx, and we know what y is. It's this function, square root of x. So we can write this as dA as x to the 1/2 dx, okay? X to the 1/2, you know, is the same thing as square root of x. So we can now substitute this into our integral form, and we get I sub y equals the integral x squared, and then we have x to the 1/2 dx, okay? And we are integrating with respect to the variable x. This is why we always say be mathematically proper. We're integrating along the x-axis. So that means we're going from the origin to this 1 meter right here, okay? So we're not integrating vertically in this example. We're integrating horizontally from 0 to 1 meter. So we're going to say 0 to... So now that we've got our integral set up from 0 to 1 meter, we can do a little bit of algebra, and we can rewrite this as integral from 0 to 1 meter of x to the 2.5 power dx. And again, remember when you're multiplying, remember it's algebra. When you're multiplying two quantities with the same base, you add the exponent. So that's how I got to the 2.5 right there. And this is a pretty easy integral, so we're going to say x raised to the 3.5 power divided by 3.5, right? Raise to the power divided by the new power from 0 to 1 meter. And we can substitute 1 into x, and 1 raised to 3.5 is still just 1. So we really have 1 over 3.5, which gives me a value of 0.286. And what are my units here? Are they just meters? No, it's meters to the 4th power. And that is my answer. So how do I get to meters to the 4th power? You may be wondering. Well, think about the formulation here, okay? You have x, which is a length, right? You have x is a length, and you're squaring it. So this x squared term carries units of length squared. And then you're essentially multiplying it by dA, which dA is a length, again, times a length. dA is a little rectangular area. So that's where you get length squared times length, and we end up with a whole quantity of length to the 4th power. And that's it. Pretty simple solution.